This is lesson 7 on hypothesis test for one average. Last time we looked at creating confidence intervals for averages. So today we're going to look at the other side of that, being able to test claims. And as a reminder, we always have the same 4-step process when we're testing claims. We state the hypotheses, we determine the model and check assumptions, we calculate the p-value. The p-value is the likelihood of our sample data or more extreme if the null hypothesis is true. And finally, we come up with the conclusion. If our p-value is low, our null must go. So whenever we have a small p-value, we're rejecting the null hypothesis. And we have the central limit theorem as our model, so we actually have pretty much this whole process here, because our null hypothesis when we're working with averages is going to be mu equals some number, and the alternative hypothesis is going to be mu and either less, that's left-tailed test, greater, that's a right-tailed test, or not equal to, that's two-tailed test, that same number. And the model that we have for the second step is it's normally distributed with a center of mu and a standard deviation of sigma over the square root of n. And what we saw last time is that if I want to be able to exchange that mu for a sample standard deviation, changing sigma for s, I'm allowed to do that, but instead of using z-scores, I have to use t-scores. So whenever I switch from sigma to s, I change z-scores to t-scores. That was the big takeaway of the lesson. There are 3 assumptions for this. Random, by that I mean that there's no bias in the way that I'm collecting the samples. I need to have independence, that means that one sample does not affect another. And if I don't have that, my backup is sampling less than 10% of the population. And finally, I need to have a large sample size. And large N means I either start with 30 or more samples, or the original distribution starts looking like a normal curve. So by that I mean if I graph this thing, it should look unimodal and symmetric. It should look like that bell shape. So we've done something really similar before in the past when we did one proportion z-test. And reminder, z-scores I found by taking value minus center over standard deviation. So when I'm looking at this new thing today, when I'm finding these t-scores, I'm still going to do the same thing. I'm going to take the value, I'm going to subtract the center, and I'm going to divide this by the standard deviation. And previously, when I looked up z-scores, I found these things on a normal table. If it was shaded to the left, I used the value in the table. If it was shaded to the right, I did 1 minus the table. If it was two-tailed, I looked at the left tail and I multiplied it by 2. I'm going to do something kind of similar today, but instead of using a table, I'm going to be looking these things up using technology. Believe it or not, we're pretty much 95% of the way done. We're just missing this new technology piece, but let's turn the page and see what it looks like from start to finish, pretty much from the get-go. So suppose that it's claimed that Tylenol lasts for 4 hours on average. After a clinical study of 30 randomly sampled patients, okay, so 30 is good, that's telling me I have a large N. Randomly sampled, that's good, that's telling me it's random. Independence, one person with a headache shouldn't affect another person with a headache. So I feel like I'm already good for assumptions, even just based off those first 2 sentences there. Mr. Wary is led to believe that the actual average is less than claimed. His data yields an average of 3.25 hours with a standard deviation of 1 hour. Test the claim. Okay, so I'm going to reread and I'm just going to highlight things. So it's claimed, this is a claim for the population, an average of 4 hours. So that 4 hours that's being claimed, this is a mu of 4 hours as my base claim. 30 random samples, I'm looking at an N of 30. I think it's less than claimed for alternative, okay, so I'm going to have less than for my HA. My data, so my data is only for 30 samples, so everything that I'm looking at here is going to be a statistic, not a parameter. So for example, this 3.25, that is going to be a sample average of 3.25 hours. That'll be my value when I'm calculating my z-score, or my t-score in this case, and a sample standard deviation of 1 hour. Since I have S instead of sigma, I'm going to be using t-scores instead of z-scores. Going to work the same way. I'm not too worried about that. For step 1, I have my null hypothesis. The claim is 4 hours. Alternative hypothesis, I think it last less than 4 hours. Tongue twister here in the morning, apparently. So for alternative hypothesis, I have average is less than 4. Second step, I have my model. As I mentioned before, I have S instead of sigma, so I'm going to be using those t-scores. When I'm analyzing my sample averages, it should have a t-distribution with some degree of freedom. Well, if I have 30 samples, remember degree of freedom is 1 less than the number of samples, with an average of mu and a standard deviation of sigma over the square root of n. Or in our case, we're using S over the square root of n because that's what's provided for us. Well, if I have 30 samples and my degree of freedom should be 1 less, that should be 29. For mu, the claimed value, the claim is always the center. In this case, that's the number 4. S is 1. N is 30. So I'm going to type this into a calculator and I'll see what I get there for my standard deviation. I've got a lot of calculators out here this morning. I'll show you why in a second. But I got 0.1826 or so. Units on this entire problem are hours. Assumptions. Well, we talked about these already, but I'm just going to highlight them again. Random. It says so. Independence. One person does not affect another. Large N. I have 30 samples, which is greater than or equal to 30. So I'm okay, but just so. So first step, hypothesis. Second step, model and assumption. I'm doing fine. Third step, p-value. My definition of a p-value is the likelihood, so I'm looking at the probability of something. My sample data, well, my sample data is a sample average. This is where that 3.25 hours comes in. Or more extreme in this case, we were testing that it lasts less, so I have a less than symbol, if the null hypothesis is true. So I'm going to try to answer this question if I base it off of the null hypothesis of 4 hours. So I'm going to draw my curve. I have 4 in the center. I'm counting by about, I'm just going to say 0.18 or so, just get a rough idea of my picture. So that's 4.18. This is 3.82. I'm detecting 3.25. That's about here. And it's 3.25 or less. So that's this little tail that starts way out at negative infinity. It actually just keeps going in that direction. And then I stop shading right here at 3.25. I'm going to calculate my t-score, and I'm going to do this the same way that I would a z-score. I'm going to take my value minus the center divided by a standard deviation. My value for this problem is 3.25. My center is 4. And my standard deviation is 0.1826. When I do this, I see that my picture is really, really not to scale. Let me type it in and see. Okay, when I just did that, I got a t-score of negative 4.11. So on this picture where I have things kind of labeled with the hours here on the top, I'm going to label the same thing with the t-score here on the bottom. This would be the number of tick marks. So 3.25 hours, if this was an x value, this is equivalent to a t-score of negative 4.11. It's the number of tick marks away from the center. So this right here is t of negative 4.11. And if I were to continue going in this direction, well, this would keep going on forever. I would shade towards negative infinity. So I've shaded between a t-score of negative infinity and negative 4.11. Now, previously, I would look this up on the table, but as mentioned last time, I would have to have a table for each degree of freedom. So I'd have to have a whole book full of tables instead of just one single table. So here's the new step. I want to be able to look up a t-distribution. And if you use your calculator for 243, you're going to find this in the same spot where you found binomial PDF and binomial CDF. I'm looking up distribution area. Since this is a shaded in region, this is going to be TCDF. So I'm going to start with the TI 83 or 84. And I'm going to hit the second button and then the bars. I'm going to scroll down until I see TCDF. And it's got the following questions that it's asking me. If I have a TI 83, it might not ask me these questions at all. I'll show you what your setup's going to look like in just a moment. But when it says low value, this is the lowest t-score that's shaded in. And it looks up the t-scores, not the values themselves. So my lowest t-score is negative infinity. So in my calculator, I'm going to do negative, and then just a whole bunch of nines to say negative way out there to the left side. For my upper value, this is my largest t-score. In this case, my largest shaded in t-score was up here at negative 4.11. And finally, degree of freedom, it essentially wants to know which one of these tables should I be looking it up on. So for degree of freedom here, 29. Now, if you're working from a TI 83, when you do TCDF, it's just going to give you parentheses. And the setup you're going to do there when you're typing in the numbers should look like my final setup here, where I have TCDF, my low value, comma, my high value, comma, my degree of freedom. I'm going to write that out here. So if I'm doing this thing by hand or wondering what the setup looks like, it is TCDF, the lowest t-score. So the lowest t-score, this is that t-score on the left side, comma, whatever t-score you have on the right side of your shaded in region, comma, your degree of freedom. So our left part of this shaded in region, well, it kept going forever. So that left side pointed towards negative infinity. And even though we never really get to negative infinity, we could just do negative a whole bunch of nines because then that's way off the table. Even if this was a z-score table, if you typed in negative 9, it's already off the table. So negative 99999, probably overkill, but that's okay. For the right side, this thing stops at negative 4.11 or so. My degree of freedom was 29. So I'm going to type that into my calculator and I'll see what I get. And then I'm going to do the same thing for a TI 89. But I just have the setup here already. And if you'll notice, I get this E-4 business. This is scientific notation. This says move the decimal place 4 spots over. So I got 1.48 E-4. So this means move it 1 spot over, 2, 3, 4. I'm going to have three zeros, so 0.1230 zeros after a decimal place, and then a 148. This is a good time to say I have a p-value of kind of 0 plus. This is a remarkably small p-value there. Let's see if it focuses better without the calculator. So when I had 1.48 e minus 4, I moved the decimal 4 places over. When I did that, that gave me 3 decimal zeros after this decimal spot, and then the 148. You could just write in these situations 0 plus when you end up with this e minus and a really, really small number. I'm okay to do the final step of this thing already, because if I have a low p-value like this, pretty much smaller than any alpha you could reasonably choose, but let's use an alpha level of 5%. If my p-value is low, the null must go, so I would reject the null hypothesis. If I'm rejecting the null hypothesis, I must have evidence of the alternative. So I have evidence that Tylenol lasts less than 4 hours. So if I wanted to put that in a commercial and say Tylenol lasts less than 4 hours, Advil lasts longer than 4 hours, at least I have evidence of half of that statement. If I wanted a more sort of bang for the buck conclusion for if it lasts less than 4 hours, how much less than 4 hours, that's really a question a hypothesis, a confidence interval would answer instead of a hypothesis test. Hypothesis test is just telling me if something is fair or unfair. In this situation, it's telling me that it's an unfair claim to say it's 4 hours. The more fair thing to say is that it lasts less than 4 hours, but it doesn't tell me how much. So whenever I have a how much style question, that's where I'm doing my CIs. I'm going to show you this on a TI-89, but it's remarkably similar. And I'm going to turn on the lamp here. I know that makes this harder to see, but this easier to see, so hang in there with me. I'm going into apps, and then I'm choosing the app that says Stat List Editor. And I'm just going to go in. Up at the top, I know this is a little bit hard to see, but there's something for F5, and it says Distribution. And I'm going to choose the option for the T distribution. For the lowest value, negative and a whole bunch of 9s. Now be careful, there is a negative button and a minus button. The negative button is underneath the 3. I'm only hitting the negative button here. For the upper value, I had negative 4.11. For the degree of freedom, this actually works identical to the TI-89. So the only thing I have to do is apps, and then I have to go stat list editor, and then F5 for distribution, and then it's the same thing as what we were just working with. And then degree of freedom was 29. When I did this, I ended up getting the same thing as before. I ended up getting a p-value of 0.000148. It didn't even put it in scientific notation for me. It looks the same as what I had earlier when I was working from the packet. Okay. I'm going to be using my 84 for the rest of the lesson here today, just because it shows up a little bit better on the camera because it's backlit. But looking at the process, step 1, hypotheses. Business as usual. I'm just using mu's because I'm working with average, and I have units, so I'm going to include those. Models, if they give me S, I'm going to use this T distribution, but otherwise it's just mu S over square root of n. When I'm finding these t-scores, I'm just thinking z-scores. I'm doing value minus center over standard deviation. To look them up, this is the new part. I have to do TCDF, the low value that's shaded in, the high value that's shaded in, and then the degree of freedom. And 4-step conclusion, as per usual, if the p-value is low, the null must go. I think really the newest part of this whole thing is kind of looking those t-scores up. So I'd like to practice that skill just a bit more with you here. So suppose I'm trying to find a t-score of 2.31 or higher, and my degree of freedom is 15. I'm going to shade in my picture, and then I'm going to write down the setup in my calculator, and I'll see what I get. So a t-score of 2.31. So if I'm actually drawing this, this tells me it's 1, 2, it's not quite 3 tick marks away, it's 2.31 tick marks away. And this thing is or more, so this is going to be shaded from this 2.31 tick marks away to the right side. So when I'm finding the low and the high when I'm doing the TCDF setup, the low value is always the leftmost part of the shaded in region. So in our case, the left side of this starts at 2.31. And it keeps going on forever. It ends in the positive infinity direction. So what you're doing, if you remember from Math 95, is this is kind of like interval notation. You're saying the start and the finish of that shaded in region. This already gives me my degree of freedom. It's 15. If this gave me a sample size of 16 instead, reminder I can get the degree of freedom by subtracting 1. I'm going to type this into my calculator and I'll see what I get. I'm going to use my 89 because it shows up a little better. Distribution, TCDF, low value of 2.31, high value of infinity, I'm just typing in a whole bunch of 9s, and a DF of 15. When I do this, I get a t-score. Well, I have a t-score of 2.31. I get essentially a p-value or an area of 0.018 or so if I round that. Let's look at another one of these. Less than or equal. So it doesn't matter if this is less than or equal. I'm still going to find the area the same way. So if I'm trying to visualize this, this is 1, 2, it's halfway between 1 and 2 tick marks down. This says or less, so I'm going to shade to the left side. So if I'm trying to figure out where does this thing start getting shaded in and where does this thing stop getting shaded in, well, it starts at negative infinity. It keeps going on forever in that direction. And I stop shading it at a t-score of negative 1.5. And I'm lucky here because they keep giving me the t-score, so I don't even have to calculate anything. I just have to type it into my calculator. So to get the area for this, I'm going to do TCDF. So the left part, or the lower part that's shaded in, is negative infinity. And I keep going until I get to negative 1.5. Good so far. If I have 31 samples, then my degree of freedom is going to be 1 less than that. I'll have a DF here of 30. So I got to be careful. Sometimes I'll have the DF, sometimes I'll have the N. I'm going to type this into a calculator. Second vars, TCDF, negative infinity, negative 1.5, and 30. This gives me essentially a p-value like thing, or at least an area of 0.072. All right, for this next one, it wants the area between negative 1.96 and positive 1.96. So this is really nice because my probability, I already can see the low value and the high value. So I'm just going to do TCDF, negative 1.96 to positive 1.96. If I have 10,000 as my N, my DF must be 9,999. I'm going to type this into a calculator and let's see what we get. That negative 1.96 and positive 1.96, that sounds really familiar, but I'm just going to type it in. And when I did that in my calculator, I ended up getting, 0.95. So my critical value for 95% was 1.96, whenever you have a really, really large n, I can't tell the difference between z-scores and t-scores. They work identically. So for a really large n like this, in the back of your head, you should be thinking, I could have actually done that with a normal table if I wanted to do that with a normal table. Let's do 2 more here. An average of 10 feet or more if mu is 8, and it's already giving me that standard deviation of 2. So let me rephrase this a tiny bit. This is saying my distribution, since it has this S here, is a t distribution. My degree of freedom, if I have 31 samples, is going to be 1 less is 30, with an average of mu and a standard deviation like thing, a standard error, of S over the square root of n. And I'm using the setup here instead of just looking it up previously by doing TCDF from the start, because I don't start with t here. I actually start with an average. So whenever I start with averages, I have to rewrite this as a t-score before I can look it up. So I'm going to fill in everything I'm told. I am told that I have an average of 8, so I plug 8 in there for my mu. I'm told that this entire thing, after they do the division, is 2. So if I draw the picture, 8 is my center. I'm counting by 2. The units here are feet, so I'll write them down at least one spot in the problem, so that way the reader knows that I know. And we're looking at 10 feet or more. So I want the probability of 10 or higher. Well, if I'm looking at the picture, I should see this already, in that this appears to be exactly 1 tick mark ahead. So I believe this is going to end up being a t-score of 1 here, and it looks like I keep shading forever towards a t of infinity. So I think this is going to be a TCDF starting at 1 and ending at infinity, but let's do a little bit of scratch work just to double check our t-score. T-score, I'm taking my value, 10, minus my center, 8, divided by my standard deviation like thing, my standard error. 10 minus 8 is 2. 2 divided by 2 is 1. Previously, I had to write this with 2 decimal places, so some of you are probably in the habit of just saying 1.00. But the nice part about TCDF is it's not limited by number of digits. So I could have just done TCDF 1 without doing those extra zeros. Likewise, if this thing had 13 decimal places after it and I knew all 13, I could include those if I wanted to be more accurate. So the calculator is more accurate than the table. TCDF starts at 1 for the t-score. I am always putting in the t. It looks up the t. It does not look up the 10. It does not look up the value. So it starts at 1 tick mark away, and it goes infinitely many tick marks up. My calculator doesn't have an infinity, so I'm just going to type in a whole bunch of 9s when it asks me to do that part. My degree of freedom is 30. Some calculators actually do have an infinity button, and if you can find it, I would encourage you to play around with that a little bit. But I think you'll find that just doing a whole bunch of 9s is pretty much equivalent. That's more than enough 9s. So I get 0.163 or so. So I just want to show you something where I had all these 9s. I'm just going to do the same thing with just 2 9s to show you how much it changes. Not at all. So when I say any large number will work for infinity, or any really, really negative, massive number in that direction would work, I mean that. So a whole bunch of 9s is pretty excessive. This is way off the table, or even just 99 would have been off the table. Even 9 would have been okay. In fact, let me show you 9. So, I mean, I'm barely seeing the difference there at 9 instead of 99. So example 6, it's not a bad idea to try to do example 6 out on your own, but just want to make a quick note. Maybe we shouldn't do this problem. Can you identify why we probably shouldn't do this problem with the information that we're given? So I think the biggest issue for me is the 16. So if my n is less than or equal to less than 30, I have a problem there. It would need to start normal in order to do this problem. And I don't have enough information to do that just yet. All the same, you're welcome to kind of go through that problem and see what you get. I think you would end up with a low value of something like a t-score of 0.2, a high t-score of 1, and a degree of freedom of 15. So you certainly could go through and do those steps. Might be good practice. It would look like example 5. But I might err on the side of caution just this once. So let's do this problem from start to finish just to see what we're working with. Subway claims that their subs are 12 inches on average. So when they say a foot long, that's what they mean. A local woman tests 100 subs and finds that their average is 11 inches with the standard deviation of 2 inches. So the claim, this is for all subs, is 12 inches. They sampled 100 subs. So all this information that she found was for a sample. So this is a sample average. The symbol for sample average is X bar. This is a sample standard deviation. Sample standard deviation symbol is S. Test the claim that the true average is less than claimed. If there's evidence, follow it up with a confidence interval. Okay. So I'm going to go through the 4-step process here. First step, null hypothesis. It's claimed that subs are 12 inches. If they're not 12 inches, I think they could be less than 12 inches on average. Second step, I'm coming up with my model. I have S instead of sigma. So for my model here, I'm going to be using t-scores instead of z-scores. 100 samples gives me a degree of freedom of 99, always one less here. My mu, my S, my root n. Well, my mu is 12 inches. My S is 2. And I'm taking the square root of 100. The square root of 100 is 10. Division by 10 just moves the decimal over, so this is T99 of 12, 0.2. Units in this problem are inches. So first step, hypotheses. Second step, model and assumptions. One sub should not affect another sub. I don't know how they collected this, so it might not be random. And I certainly have a large n. I'm working with 100 subs. That's more than 30. So I feel okay about this, but I might want to follow up and ask, hey, where did you get all these subs? Because if it's from the same store, then I can only really say that that one store is unfair instead of all Subway stores. So your conclusion is sort of limited by where you sample. Third step, though, p-value. The p-value is the likelihood of my sample. Well, my sample, my model tells me, is I'm going to be looking at sample averages X bar. And my average was 11 inches. So the p-value is the likelihood of my sample data, or more extreme, in this case means less. So I'm using this value 11. If the null hypothesis is true, I'm going to use this value 11 compared to the claim of 12. So 12, and I'm counting by 0.2, so this is 12.2, this is 11.2, and I see a bit of a problem because if I'm counting by 0.2, it's going to take me a long time to get down here to 11 inches. In fact, it's going to take me at least 5 of these tick marks down. I'm concerned about this amount or smaller for sandwich size, so I'm shading to the left direction. So my t-score, I'm taking 11, my value, minus the center of 12, and I'm dividing it by that standard deviation-like thing, called standard error to be a bit more precise. And when I type this into my calculator, I get -5. -5 is the t-score, so when I'm doing the t-CDF, my lowest shaded in t-score, while this keeps going on towards -infinity, my highest shaded in t-score, if I'm just thinking about the bounds for this shaded region, the highest part there was -5. And I'm always doing the t-scores when I'm looking up the t-CDF. So from -infinity to -5, this is going to be really, really small. It's really far out there. And my DF was 99. So in my calculator, I'm doing my second vars or my stats list editor, and then I'm choosing F5 for distribution. I'm choosing t-CDF, -infinity for the low value, comma, -5 for the high value, comma, my degree of freedom is 99. When I do this, I get 1.24 e minus 6. So this would mean I have, moving that decimal over, 1, 2, 3, 4, 5 zeros, and then a 1. When you're in this situation, you can just call that 0 plus, and that should be fine. So if you have a ton of zeros and then a number, let's just call that 0 plus. Final step, conclusion. If my p-value is low, and it is, it's smaller than pretty much any alpha level you could want, I'm going to use an alpha of 5%, because this is about sandwiches, so I'm not super concerned. Now, if she wanted a lot of evidence for her court case, she might want to use a really small alpha level like 0.01, because she might want to be really, really confident in her results. All the same, our p-value is less than alpha. We reject our null hypothesis. So we have evidence, ... that the average sublength at this subway, whichever subway she happens to be sampling from, is less than 12 inches as claimed. So if she wanted to follow up with a lawsuit, I suppose she could. She has evidence of unfairness there. I'm going to do a 90% confidence interval as a follow-up. I'm at least going to set this up. I'm going to ask that if you're doing this at home, try to pause the video and do this on your own. And I would ask that you try to pause it now. Okay, I'm going to go through it. Confidence interval, I have center plus or minus my distribution star multiplied by my standard error. The nice thing is I actually know a lot of these numbers already. So my average was 11. I'm more inclined to believe an average of 11 since I rejected that average of 12. So I always base my confidence intervals based off of what I'm experiencing. I'm using my sample there. If I have a DF of 99, when I looked up the 90% in my table, I got a critical value of 1.66 or so. And I already know what this s over the square root of n is because I did that calculation up top. That was 0.2. When I type this in with the minus, for the low side, it gave me 10.688 inches. That is less than 12, so that's reasonable. 11.332 as the high, that's also less than 12. That's to be expected because I had evidence that it was less than 12 inches on average. Now, evidence that it's less than 12 inches, that was a little bit of a lackluster conclusion because it's not super specific about how much. This is what I mean by following up with confidence intervals way more descriptive. It tells me how much it is unfair. So I'm off by anywhere from an inch to an inch and a half for the sub length. I could be reasonably upset about that if I truly value every inch of sub that I get from Subway. I personally think there are more important things to get frustrated about, but you do you. Okay. So I want to do just one more problem with you. So I'm going to do this example 8. Claim the average PCC student takes 13.2 credits. Let's test it. So let's say I collect a sample and I get a sample of 10, 12, 15, 14. And I'm told the original distribution is normal. So I'm not going to worry about the assumptions on this one. I just wanted to show you one problem where you have some raw data, just as a reminder of what you need to do from the start. So you have to calculate the average for the sample. So to find the average, I'm going to take these four numbers and I'm just going to add them up. And divide by the number of terms. In this case, I only did 4 samples. And I get an average of 12.75. And I'm finding that I spend just like way more time on the setup than I do the actual problem. I'm looking at 4 samples, so my degree of freedom is going to be 3. I want the standard deviation. Before that, I have to find the variance. Variance, I take the first value in the list minus the center squared. I add all these things up to the last value, 14 minus the center squared. And I divide this by the number of gaps or the number of commas. So I have 1, 2, 3 gaps. That's actually what the df is. So the df is telling me what the denominator should be, n minus 1. When I type this into a calculator, I get something like 4.915-ish. In order to get my standard deviation, I need to take the square root of this variance number. When I take the square root of this, I get an S of about 2.217 or so. My units for this entire page up here, credits. So let's test the claim that it's less than 13.2. So for first step, they're claiming an average of 13.2 credits. This will be the last time I write down units in this problem. Alternative, less than 13.2 credits. Second step, we'll come up with our model. We have S, so when I'm coming up with this model, I'm going to be using t-scores. My df is 3 mu s over the square root of n. My mu is 13.2. My s is 2.217. My n is 4. So when I take the square root of 4, that's just 2. So I have 13.2 comma. So I have 2.217 divided by the square root of 4. I have a standard error, standard deviation like thing for my model of 1.107. Third step. My p-value is the likelihood of my sample average. While my sample average was 12.75 or less, I'm going to have this thing shaded to the left. So I'm drawing my picture. Picture's mostly here as a rough guide. I have 13.2 in the center here. I have 12.75 here, and I want this much or less, so I'm shaded to the left side. Now, before I can look this thing up, and I know when I look this thing up, it's going to be TCDF. The lowest part that's shaded in is negative infinity. my degree of freedom is 3. I don't know this number here yet. I don't know what this large t-score is, because as a reminder, I'm not using the values, I'm using the number of tick marks away. I'm using the t-scores when I am looking up TCDF. So I'm going to find my t by taking my value, 12.75, minus the center or claim of 13.2. And I'm dividing that by the standard deviation-like thing, the standard error, of 1.107. When I did this, I got a t-score of negative 0.407 or so. And you'll notice that I can get away with using more decimals. I don't have to round this thing to just 2 decimals anymore. Here I'm using 3. Negative 0.407 will be my high t-score there. So in my calculator, I am doing TCDF negative infinity to negative 0.407, a DF of 3. This gives me a p-value of 35.6% or so. This is a fairly large t-score, so for 4-step conclusion, if my p-value ends up being larger than, let's say, an alpha of 5%, I would fail to reject the null hypothesis. So I do not have evidence that the average number of credits that a student takes is less than 13.2 credits. So this 4-step process, just the same thing that it was for proportions. The only thing that's changing really, the model, but in a lot of ways this model is nicer than my proportion model. And I'm looking things up using TCDF instead of a table. Now, if you were wondering what would happen if instead of equals, this was not equal for the alternative hypothesis, just testing for a difference, and I would say that might even have been a more reasonable setup. If you weren't sure what's going on to start out with, maybe you're wondering, could it be less or more? Well, keep in mind what this picture is going to look like. This is going to have a two-tailed test. So in this situation, I need 2 times either the left tail or the right tail. Well, in this last problem, we just found the size of the left tail. So previously we used to do 2 times the table. Now we're just going to do 2 times the CDF on the left side. So I'm going to have 2 times the area of the left. It's the same setup. I just need to remember to multiply by 2 whenever I have a two-tailed test. And if I thought I had a large p-value before, I have an even larger one now at 71% or so. So that would be a massive p-value there. I would fail to reject the null hypothesis for sure. I do not have evidence that the average is less than 13.2. That's all for today. We've now looked at both confidence intervals and hypothesis test for a single average. What I'd like to do in the upcoming lessons is to be able to compare 2 averages, a mu1 and a mu2, using both a confidence interval and a hypothesis test, so I can see how maybe the number of credits for PCC students compares for the number of credits for PSU students. So I want to be able to compare averages for multiple groups, and that will be coming up next time.